All right. Good afternoon, everyone. So I think we shall start. So maybe you have noticed our homework 2 has been released, but we do have plenty of time to do that. I don't want you to spend time on homework 2 during the spring break. So if you can do it early, hopefully. Oh, what's wrong? Okay. Hopefully, like you can submit the homework assignments before the spring break. Although the due is the following Tuesday of the spring break. Again, the work amount for this time is not very heavy. It's not very heavy. You can choose to work it early rather than spend any time during the spring break. Again, I mean, highly encourage everyone to leverage the office hours and seek for help. And yeah, and again, every time when I stay in the office hour, there are only 1 or 2 students swing by, and then I just wait there in front of my desktop. No one come, right? If you like to talk to me about homework assignments, about anything, and other things like project, even including project, feel free to do that. Okay. Okay, so let us continue with the probabilistic graphic models. So in the last lecture, we have introduced the general definition of directed graphic models, which is also referred to as Bayesian networks. Right? So remember, we use nodes to represent random variables. Right? And if there is an edge connecting one node to the other node, that means there is a conditional probability, right? So if one node has multiple parents, it just means, okay, they're associated with, it is associated with a conditional probability condition on its parent nodes, right? So, and we stressed on the fact that actually the graphic structure represents a decomposition structure of the joint probability, right? In other words, the simpler the structure you have means that the more information, the more knowledge you know about this joint probability, right? If you don't put any simplification about structure, that means your graph is kind of a fully connected graph. It actually doesn't have anything. Right? It's much harder to learn. However, if you have some prior knowledge, you have some experience, you have some strong beliefs to greatly simplify structure that not only encode your knowledge, but also helps the computation, including training and prediction, right? And then we talk about a question, right? So for a complex Bayesian network, right, given an arbitrary non-intersecting sets of nodes, A, B, and C. A, B, C are 3 sets of nodes or random variables. We want to ask if condition on C, the variables in C, A and B are independent or not. Right? So this is not a trivial problem, but it does reflect the underlying properties of your graphic model. So we mentioned that there is a general, very efficient algorithm that can tell you if this condition independence holds or not. Right? But we're going to start with our basic structure. And later we'll say the general algorithm framework, which is called the Bayes-Ball algorithm, is just repeatedly test if you have met the 3 basic structures, then decide if the conditional independence is correct or not. Okay, so we talked about 2 basic cases in the last lecture. One is called tail to tail. So basically you have these 3 random variables or nodes, A, B, C. C is in the middle. So it is called tail to tail just because if you draw a path from A to B, right? So you're gonna first meet C with the tail of the edge, right? And you pass through C, you meet another tail. That's why it's called tail to tail. And this basic structure tells us that if A and B condition on nothing here, right, then A and B are not independent or dependent. Right? However, if they are conditioned on C, meaning that the node C has been observed, namely shaded here, right? Then we can safely conclude that A and B are independent condition on C. Right? So we have shown why this is true. Right? So I'm not going to repeat this, but again, I encourage you guys to do this manual analysis like me. Right? That will help you deepen understanding this fact. Right? And the second case is called head to tail. Right? So again, there are three nodes, A, B, and C is in the middle. But we're going to connect from A to C first, and then connect from C to B. So when we draw a path from A to B, you see that we're going to first meet C with the head of this arrow, right? And then we leave C with the tail of the next arrow. So that's why it's called head to tail. And the conclusion for the head to tail structure is exactly the same as that for the tail to tail. Namely, if condition on nothing, A and B are not independent. Oh, they're dependent. If condition on C, the A and the B are independent. So again, we can do some kind of analysis, right? So if you want to test if this is correct, right? You just need to look at the joint probability, right? The joint probability of A and B, right? To do that, you have to marginalize out C in the joint probability of A, B, and C, right? And according to the graph structure, right? So this guy tells us we have a P of A times P of C given A, right? And this guy tells us we have a conditional probability of B given C, right? So you see that actually C appears in these two conditional probabilities which couples A and B. So when you do the integration, you cannot factorize the integration result as a term which solely contains A and the other term solely contains B. That's in general not possible. However, if you look at the second fact, that is, given C, whether A and B are conditionally independent, right? If you calculate this according to this structure, it's fairly easy to show that this is essentially this conditional probability of A given C times conditional probability of B given C. I will leave it as an exercise for you to verify this. Okay. Following the same idea to do analysis for the tail-to-tail case. Okay, this is the second basic case, right? So then let us look at the third basic case, which is a little odd. The structure is called head-to-head. Why it's called head-to-head? I mean, same reason. If we draw a path from A to B, you see that you're gonna meet C. I mean, you're gonna meet C first at head and leave C at the head as well. So that's why it's called head-to-head. And in this case, the conclusion is opposite. So basically, if A and B condition on nothing, then A and B are independent. Right? So this is fairly easy to see, right? Because if you look at P of A and B, right? Again, you do the joint probability, right? So this guy, from the graph structure, the joint probability of ABC is equal to P of A. Remember, A doesn't have the parent node, right? And also P of B. B doesn't have a parent node as well. And then C has two parents, A and B. So there is a conditional probability P of C given A and B. Now you just integrate C, right? So you can see this guy's, you can just move this marginal probability outside. You do the integration, it's simply 1. Right? So it gives you this factorization, P of A times P of B. So it is easy to see this. However, if you condition on C, it is easy to see that actually A and B are not independent anymore, because C couples A and B. You cannot factorize them anymore. So, so here's the difference, right? So for the first two cases, tail to tail and head to tail, once C is observed and conditioned, then A and B are independent.
If A given C is just P of A.
What?
P of A given C. It's just P of A according to the structure.
Yeah. Oh no, I mean, you're saying P of A and B given C is P of if you want to say the condition independence another way, it should be like that. P of A given B and C is equals to P of A given C. It's not P of A itself.
No, I mean the right side is P of A given C times P of B given C.
Yes.
Just P of A given C is just P of A according to the structure. Is it true?
No, it's not true. P of A given C is P of A and C divided P of C. You shouldn't say it is just P of A. That just means C and A are independent. Or actually, they're, I mean, given this graphic structure in general, not independent. Okay. So for the tail to tail and head to tail, once the intermediate nodes C are observed, we see A and B are independent, meaning conditionally independent. Once C is not observed, I mean, is conditional on nothing, then A or B are dependent. But for the head-to-head case, the conclusions are just opposite. If C is not observed, meaning that it's conditional on nothing, then they are independent. Otherwise, if the intermediate node C is observed, then usually they are dependent. So just to be aware, there's a difference here. So for this head-to-head structure, we also want to introduce a known effect. It's called explainer wave effect. So it's a well-known property of Bayesian networks. So what does it mean for explainer wave effect? We use a concrete example to illustrate it. Right? So now we assume we're looking at your car. You know, you have the read about oil, right, or the fuel. So we have a gauge. When also we have a fuel tank, right? And also have battery. Right? So there are a relationship, obviously, between the battery, the fuel tank, and the gauge. So once you, but for people, like for drivers, we're not professional technicians, right? So we usually look at the gauge rate. If the gauge rate says, okay, you have a zero rate, we're kind of like in trouble, right? Maybe your fuel tank is empty, but it's not always like that. For example, if your battery is dead, it also possible to give a zero rate in the gauge. Why? Because your sensor is driven by the battery. So that means our rate of gauge is not only dependent on the actual amount of fuel, like in the fuel tank, but also dependent on the status of battery. So here we build up a head-to-head simple Bayesian network to model them, right? So we have a distribution over the battery status, right? Battery is either alive or dead, right? We also have the binary fuel tank status, right? One means that the fuel tank is still not empty, right? You still have some fuel. And zero means your fuel tank is really empty. And then both the battery status and the fuel tank status decides the rates, the gauge rate, right? So, I mean, for simplicity, we assume, okay, we got two status of the gauge rate, either is non-zero or zero. So here is our specification of this model. We the probability of your battery is alive is 0.9, and the probability of your fuel tank is now empty is 0.9 as well. And then condition on different status of the batteries and the fuel tank, we have different probabilities of a non-zero read of the gauge. They're just listed here. So what you can see that, okay, if your battery is alive, condition on battery, the battery is alive and the fuel tank is not empty, then there's a large chance that your gauge rate is non-zero. But there's still a small chance that your gauge is measured incorrectly, like give zero rate. It is possible. And that is corresponding to the second case, right? So given your battery is alive, but your actual fuel tank is empty, you still have a small chance, which is 0.2 here in our model. You still have a non-zero gauge rate. However, if your battery is dead, given your battery is dead, even your fuel tank still has fuel, it's not empty. The chance that your gauge rate is non-zero is relatively low, it's 0.2. And of course, like if both the battery is dead and the actual fuel tank is empty, then there's an even smaller chance that you get a non-zero read. So this is just a specification of the model parameters. So here we want to mention an interesting phenomenon that is given this model. Suppose in the first case, we just observe your gauge rate is zero. You don't know the status of battery. You don't know it is alive or dead. Then we can calculate the posterior probability that your fuel tank is empty is approximately 0.257. But this case in general includes or internally comprised of two cases. One is battery alive, one is battery dead. So now, if you further observe that your battery is dead, then condition on the fact that you have a zero rate in the gauge and dead battery, then you calculate the posterior probability that your tank is empty. Now, this probability is reduced to 0.111. So you can see the first posterior probability is larger than the second posterior probability. This phenomenon is called explain away effect. That means our probabilistic explanation of why the zero gauge is partly taken away from the fact that the battery being dead. This is the reason, right? If you don't know battery is dead, okay, you consider both the case that battery is dead and battery is alive, so you have a larger chance, right? So now you have observed the battery has already been dead. You know that, okay, battery is dead has taken away part of the possibility that you have zero gauge, right? So your chance of your fuel, your actual fuel tank is empty is even lower. So yeah, this is the basic property of the Bayesian network, and actually it fits our understanding of this relationship between those these variables. Right? Any question? Mm-hmm. Oh, it's non-zero. G is 1 just means you have non-zero read of your gauge. Here, here it tells us that if you haven't read your gauge, right, it simply give you 0. You cannot worry about okay if your fuel tank is empty or not. Yeah, the gauge is empty, meaning that indicating the fuel tank is empty. But actually, whether the fuel is empty or not, is not. I mean, it has some probability that the gauge rate is 0, but the fuel tank is not empty. So once you observe that the battery is dead, so you can imagine that okay, the battery dead partly explains why the gauge rate is 0. That's why you condition both observations. Your probability, the tank is empty, is reduced. So previously, before we have observed the battery is dead, we don't know that. Well, we kind of attribute your observation, the reason that you have 0 gauge rate, mostly because of your tank is empty. Right? But now you have observed the battery is dead. That means the battery is dead. This fact kind of take part of the explanation why your gauge rate is empty. The gauge rate is 0. So then you compute the probability that your tank is empty. Now it's reduced because its explanation is kind of partly is taken away by the battery is dead. Does it make sense? That's an interesting observation for Bayesian networks. Right? I mean, some textbooks will tell you, okay, this is not good, but for me, I think it's pretty natural. It's kind of like a fit what human beings thought about or explain things. So now let us go back to the head-to-head structure. Right? So actually, head-to-head has is a more general case. You can show that if C, the direct descendant of A and B, is observed, or any of the descendants of C is observed, then A and B will no longer be independent. And it is easy to show that. I'm not gonna highlight how we prove that. As long if you can show that condition on C, A and B are not independent, and it is easy to see to show that condition on any descendants of C that is observed, then A and B are not independent as well. We see that because they are all coupled. A and B are always coupled by this chain of conditional probabilities. So now we have talked about 3 basic structures, right? And head-to-head, tail-to-tail, tail-to-head, and head-to-head. To answer the general question, given arbitrary 3 non-intersecting sets of nodes A and B and C, how do we test the conditional independency? Right? Can we answer if condition on C, namely all the nodes in C are observed if A and B are independent? Right? We're going to use this so-called baseball algorithm. Right? So you can imagine, because we're representing all the things in our network, right? So you can imagine you kind of like throw a ball going through every path from any node in A to any node in C. If under some conditions these balls are blocked, you're going to try another path. If you try all the paths, if every path is blocked, then you can see A and B are conditionally independent on C. Otherwise, A and B, the two sets of nodes, are not conditionally independent. That's the basic idea. So let us look at the algorithm steps. So first, in this graph, we're going to shade all the nodes in C. Okay? So imagine there's a bunch of nodes in A, there's a bunch of nodes in B, right? There's also a bunch of nodes in C, right? So we're going to shade all the nodes in C. Then we just look at every path from any node in A to any node in B. Okay? So there could be many paths, right? From any node in A to any node in B, right? Many such kind of passes. Right? Some paths will cross the nodes in C, some paths will not. Right? And I want to answer the question that if C is given in B are conditionally independent or not, right? How can we do that? We just look at every path from any node in A to any node in B. And we just look at every node along this path, right? Every node along this path. If the path contains a node such that the arrows on the path meet head to tail or tail to tail at the node in C, then we can claim that the path is blocked. And then we continue on to the next path. Or if a node, the arrows on this path meet the node with the style head to head, as we just discussed, the third basic case. But neither the node or any of its descendants in C, we can also say, okay, this path is blocked. And then we move on to the next path. If every path you can find a node that match the three basic cases as we just discussed, right? That means the blocked path. If every path is blocked by some node, then we can claim condition C and B are independent. However, as long as one path you don't have any node that can block that path, then you should stop and then claim that this conditional independency does not hold. That's the idea. So again, why this called baseball? Okay, we were like, okay, I'm gonna look at every path from the set A, from any node in set A to any node in set B, right? And just we just starting from the beginning node and roll this ball, right? And along a particular path, as long as there's one node which satisfy or match the three basic structures as we mentioned, right? That means that path is blocked by the node and your ball is stopped. You have to bounce back and look and starting from another path and try this again. If it turns out that every path which connect A and B are blocked, then you can see A and B are conditionally independent on C. Otherwise, you just say A and B are not conditionally independent. Does it make sense? So I mean, one of critical contribution of Professor Julia Kerr is to show why this is correct, why this baseball algorithm is correct. Well, we're not going to cover how he shows that, what is proof. But here we want to give two concrete examples where we can apply baseball algorithm to test the conditional independence. So the first graphic model is like this, right? So our node set A just contains one node, right? This is A, and the B is this node, right? And C is this node, right? And C is shaded. So to test if A and B are conditional independent given C, right? according to this Ball algorithm, as we just mentioned, we just need to enumerate every path from any node in A to any node in B. Okay? So there's only one path from here to here. Okay? Just one path. So then we just look at every node on this path and check if any node matches the three basic structures we have just discussed, right? So we can first look at E, right? So the node E actually meet the head-to-head structure, right? And when we talk about head-to-head, we know that if any of its descendants are not observed, then the parent nodes are conditionally independent, right? Here, unfortunately, the descendant node C here is observed. So meaning that these nodes and these nodes are conditionally dependent. That means this node fail to block the path, right? So we're gonna look at the next node, F. And F here have the structure, it's called tail to tail, right? However, F is not observed. F does not belong to C. That means the parent, the nodes which connect to F directly are dependent. It's not independent. That means F does not block the path as well. Then there's not any other intermediate nodes on this path. So basically says this path is not blocked by any node, right? So that means this conclusion does not hold. Does it make sense? Any questions? Or is it relatively trivial? You change what? E to F. Yeah, that will work. Yeah. Because that will meet the second structure, right? The second basic structure is called head to tail, right? Head to tail, and that means. Oh no, sorry. It's head to tail. That means E must be observed. If E is also belong to C, that means condition independence. It doesn't include the descendants. So let me just make this a little bit change. So suppose our C set contains not the small node C, but also F. Now can we conclude A and B are conditional independent given C? Can we? I mean, now I'm kind of enlarge the set C. So I'm including not only the small node C here, but also the F node here. That means both C and F are observed. Yeah. It's still on this. The definition of light. The definition of what? Light. Previous slide. We just want to ask, right? If all the nodes in C are observed, if A and B are independent. So the first
condition said that the only path is black, so they are conditionally.
Yes, exactly. Right. So if you just imagine like you throw a ball, right? You find one pass. You want to see if the ball starting from A can safely arrive at B. It's not blocked. So as we mentioned that when you look at if the ball arrives at the node E, look, E is the head-to-head structure, right? And we know that condition on any of its descendants, the two intermediate neighbors will not be conditionally independent. That means E cannot block the path. Right? Yeah, and then we move to C, we move to F. And look at F, right? F is tail-to-tail structure, right? And now it matches the tail-to-tail structure, the conditional independence, right? Because F is observed, that means the neighboring nodes E and B are conditionally independent, meaning that this path is blocked. So that means your ball is stopped here. You don't have any other paths. That means all the paths between the nodes in big A and nodes in big B are blocked. So we can conclude that in this case, A and B, big A and big B are conditionally independent. Does it make sense? Mm-hmm. Yeah. Oh, it's here. Mm-hmm. Yeah, C is descendants of E. Yeah, if C is observed, then it does not block. If C is unobserved, then it blocks. This is different from the head to tail and tail to tail structure. As long as you have an intermediate node which matches the head to tail and tail to tail structure, that node, as long as shaded or observed, then it is blocked. But here, for the head to head structure, there is a little bit special things here that if you want D to block this structure, you have to ensure all of its descendants are not observed. It's kind of like opposite to the other two basic structures. That's something a little bit subtle here. Mm-hmm. Yeah. Yeah, that's because E does not block the structure, but F blocks. That's why when we include F in C, we can conclude it is conditional independence. Okay, so there's a little bit subtle difference when you apply the baseball algorithm. Right? Just be aware, be careful about the difference between the head-to-head structure and the other two structures. Otherwise, it's just just enumerate the paths and look at if this path is blocked or not. And again, if you look at the second structure, so it's pretty straightforward to see that now A and B condition on C is independent, right? Because both E and F are blocking the path. Right? Because right now C is not included in this big C set. That means E blocks the whole path. And also F is observed, then F blocks the whole path as well. Okay, any question regarding the baseball algorithm, this kind of things? And hopefully our examples have given a clarification. Okay, so the next concept we want to introduce is called Markov Blanky. So what does it mean? So consider we have a Bayesian network with big D nodes, x1 to xd, right? And for a particular node xi, we want to ask condition on what set of variables, right? Xi are independent to the remaining variables. So you can imagine like this is xi, right? And the remaining variables other than xi can be partitioned in two groups, A and B. So we say A is Markov Blanky if condition on A condition on A, B are independent to Xi. Okay. So how to see who constitute the Markov Blanky? If you look at the posterior distribution, right, we can see some clue. Right? So the posterior distribution of Xi given all the remaining variables. So this should be represented as A union B, right? It is the joint probability of X1 to Xd divided by the marginal probability of A union with B, right? So this is just the integral of the joint density with respect to Xi. So according to the Bayesian network structure, we know that the joint probability is decomposed as the product of a series of the conditional probabilities, right? And similarly, in the integral, marginal distribution, right? So you can imagine for any conditional probability terms, as long as Xi appears in this conditional probability, and all the other variables which coexist in this conditional probability are coupled by Xi because you're going to integrate with Xi. Right? And if there is a particular conditional probability which does not contain Xi at all, they're constant to Xi, right? So you can move it out to the integral. And you have same term in a numerator, right? They just cancel out. This actually tells us the Markov Blanky A here are just those random variables which coexist in the conditional probability terms that include Xi. Right? This is called Markov Blanky. So who will coexist in the probability, conditional probabilities that include Xi? Right? You can imagine it will include Xi's parent. Right? So if you have a conditional probability of Xi given a bunch of variables, say X1, X2, right? Of course, X1, X2 coexist with Xi in this conditional probability. They are coupled. They're coupled in this integral. They cannot escape from the integral, right? Or X as children, right? If you have a conditional probability which is conditional on Xi and something like X4, right? X4 is coupled with Xi. Or the children's co-parents, like you have something like that, you have Xi and the co-parents like X5, right? X5 and Xi are coupled. So all those variables consist of the Markov Blanky. If you look at the network structure, the Markov Blanky are just those shaded nodes, all the parents, the children, and the co-parents. And if you have other nodes, right? So let me use other color. For example, here, and here, and here, right? So condition on those blue shaded nodes, Markov Blanky, and the green nodes are condition independent Xi. So you can feel like it's like a wall like separate Xi and all the remaining variables. Okay. So now we have given a general introduction of Bayesian network definition, the basic properties, and also how do we examine the conditional independency and the three basic structures which they call it D-separation. Right? So this separation is a bit subtle to test conditional dependency because for the three basic structures, the head-to-head have an opposite conclusion to the other two, tail-to-tail and head-to-tail. Right? So it's a bit subtle. So a natural question would be, can we have an easier graphical representation allow more natural tests? Right? Like, can we just get rid of the influence of the directionality of the path? So can we just based on path without considering arrow directions? This leads to another type of graphic models, kind of undirected graphic models. So imagine you're going to define your joint probability over undirected graphic models. There's no directed edges. All the edges are undirected. You don't have arrows here. So naturally, we would imagine that if we want to test if A and B are conditionally independent C, we just look at if all the paths from A to B are just blocked by C. That's it. Right? We don't need to consider if it means heads to heads or tails to head. And in different cases, the definition of the blockage is different. Right? But here we just look at, okay, you know, this C, these two nodes are blocked. That means, okay, the paths from any nodes in A to any nodes in B are just blocked. This will be a lot easier to test the conditional independence. Right? And also, if you use undirected graphic models, the Markov Blanky, you don't need to differentiate what is parents, what is descendants, what is co-parents. Right? You just look at all the neighboring nodes. They will consist of your, they will constitute your Markov Blanky. So how do we define an undirected probabilistic graphic model? So that will need us to look at some basic structures on the undirected graph, which is called cliques. Cliques is just a subset of nodes in a graph that every pair in this set is connected by an edge. This is called clique. Okay? So for example, the pair x1 and x2, they are cliques. Why? Because there's only one pair, x1, x2, and they are connected by an edge. Okay? And x2, x3, and x4 are clique. Is a clique. Why? Because for every pair of the nodes in this set, which include x2, x3, x2, x4, and x3, x4, they're all connected by the edges. It's called clique. Now I want to ask, is x1, x2, x3, x4 a clique? No. Why? Yeah, because x1, x4 are not, there's no edge between x1 and x4. So it's not a clique. So based upon the definition of clique, we can define the maximum clique. Maximum clique, it just means if the set of nodes is clique, then you cannot add one more node to get another clique. Like x2, x3, and x4 is a maximum clique. Why? Because you add any an additional node like x1, it won't be a clique anymore. Okay. Is x1, x2 a maximum clique? Why not? Yeah, if you add x3, it still is a clique, right? So it's not maximum clique. So given an undirected graphic model, right? The joint distribution, again, we're gonna assume each node in this undirected graphic model is a random variable. Then our joint distribution is defined on the product of the maximum cliques the product of the potential function over the maximum clicks enumerated over this graph. That's how we define undirected graph. In other words, if you want to associate this undirected graph model a probabilistic distribution, you have to define a potential function over each maximum click. Here it will include x1, it will include x1, x2, x3, and x2, x3, x4. Two maximum clicks. You just define two potential functions on this two maximum clicks, and then you do the normalization. So this is the associated joint probability over this undirected graphic model. And this potential function is non-negative. Right? This is very natural, right? You don't want this product to be less than 0, otherwise it's not a probability or probability density. And then the z, here is a normalizer, is also called a partition function. It's similar to the definition in the exponential family. It's just sum over all possible values of c across all possible values of the random variable or nodes across this undirected graphic models to normalize this product to ensure this is a valid probability distribution. And somewhat like if you have a physics background, you might have already seen these undirected graphic models for statistical physics. Okay? So they define the potential function as energy of those molecules. They follow some structure. And here exponential, right? They call this Boltzmann distribution. But here in computer science, well, we actually don't care too much about the physical meanings. Okay, so any questions so far for this general definition of the undirected graphic model? Okay, it's pretty straightforward, right? Okay. So for undirected graphic model, you even do not need to worry about if there is cycles, right? Doesn't matter. They're just some functions over the maximum clicks. So here I want to give an example, a concrete example, as an instance, right? One very popular application is called image denoise. Right? So suppose this is your ground truth image, right? And they're unfortunately corrupted by some noises. So this is what your observed image. So you want to denoise this image and to get a clean version as good as possible. How can we do that? And we can construct an undirected graphic model. Right? Remember, image is just an array of pixels, right? So we can view each pixel as a particular random variable. Like here, for simplicity, we can just assume, okay, this pixel is either 1 or 0, right? And 1 means that it is yellow. 0 means it's just blue. Right? But in practice, well, it can be more complicated, like RGB values. Right? And for each pixel, we assume, okay, there is a latent random variable xi, which indicates the underground truth. Like it should really be the blue pixel or the yellow pixel. Right? And then the associated with each xi is y is actually observed pixel value. So this is a kind of noisy observation because you can see that many pixels are corrupted, meaning that this is supposed to be a yellow pixel, but it's corrupted and flipped into a blue pixel. Right? And then between xi, because we know those image, each pixel is neighboring with the surrounding pixels, right? So we can construct a graph. Right? We just make an edge between every neighboring pixels. This is our graphic structure. Then, based on this graphic structure, we can define our potential function. Right? So the potential, remember, each maximum click right now is just every pair of the pixel, right? So our potential function will be defined as, first, we're gonna multiply the random variable xi by some scale h, and then multiply the pair, the product of its surrounding pixel, xi, xj, in its maximum click by beta, and then multiply xi with its observation yi with another coefficient eta, and then we take exponential. So this is my potential function definition. Right? So intuitively, why should we do that? We just want to capture the relationship between the latent random variable and its observation, which is here, right? And the relationship between xi and its neighborhood in its maximum click, and also some intrinsic property of xi itself, as we have this. We just do a linear combination, well, which is really a simple model, right? And we just multiply this potential function together, we got this form. And then once we have this model, because we have already have observed yi, right? We want to compute given the observed noisy pixel values, what is the value of x? It becomes a posterior inference, a posterior probability estimation problem. So, so here is our estimated posterior probability. So those values are just estimated latent random variable x rather than y. Okay, so you can see a lot of noisy pixels are recovered. So any questions so far? Okay, but I just want to emphasize x are binary, y are binary. If you want to compute this posterior distribution, it's not a trivial thing. It's actually quite challenging, and later we'll discuss the general framework to do this more efficiently. But here, let's just assume, okay, we have this model defined, and how do we compute this? And we have some efficient algorithm to compute this posterior probability. And here is just the result to showcase, well, this undirected graphic model is really useful. Mm-hmm.
Right, so just consider the value of x which maximize the solution.
Yeah, yeah. I mean, if do a full Bayesian inference, you want to get this posterior distribution. But if you want to use that to recover, right, you really use the expectation of posterior distribution, or you just maximize the likelihood. Yeah, this is maximum likelihood. It's called ICM algorithm. So ICM algorithm not only estimate x, but you also need to estimate h and beta, eta. This all parameters, all these parameters jointly. But just to give you a sense, like this is not easy because h, beta, and eta are continuous variables, right? Continuous parameters. But xi are just binary. So it's kind of mixed optimization of binary variables and continuous variables. It's not easy. And not to mention that you want to calculate posterior distribution of those binary variables and also the model parameters. That's even more challenging. But later we'll discuss. Like for example, you can use the variational Bayes framework to do this quite efficiently.
So about ICM.
No, ICM is kind of like a very classical algorithm in image processing. If you have taken that class, you should have heard that. But we're not going to talk about this because this is typically is not a Bayesian framework, but it's pretty straightforward. Okay, so now we have given two definition of two types of graphic models. One is called directed graphs, the other is called undirected graphs, right? So natural question would be, can we convert a directed graph, which is Bayesian network, to an undirected graph? So things becomes quite easy. However, reversely is quite hard. So let us consider how to convert a Bayesian network to an undirected graph. So we can look at this chain model, right? So as our previous example, right? So from this Bayesian network, our joint distribution is written as P of x1 times the conditional probability of x2 given x1, then conditional probability of x3 given x2, and blah, 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 until the conditional probability of x big N given x big N minus 1. Right? So if we want to convert it to an undirected graph, right? First of all, we just look at which variables are coupled. So first, P of x1 and P of x2 given x1, that means x1 and x2 are coupled. So we should have an edge between x1 and x2. Okay? And similarly, we know that from P of x3 given x2, we know x2 and x3 are coupled. So there must be an edge between x2 and x3. So you continue to do that, you find that you should successively connect each random variable, each node, and its next node. Okay? So it's kind of similar structure to the original Bayesian network, except that we're gonna delete the arrows. And correspondingly, our potential function are just multiplying the corresponding conditional probabilities. Okay? That's it. But this is just one simple case, right? In general, in addition to preserving the original edges, we also need to add more edges to ensure this is a maximum click. Remember, our undirected graphical model is defined on maximum clicks. Right? We need to ensure this is a valid click. For example, for this Bayesian network, we know it tells a joint distribution in this way, like P of x1 times P of x2 times the P of x4 given x1, x2, x3. So that means from this conditional probability, we know that x1, x2, x3, x4 are coupled together, right? So they should belong to one potential function. That means x1, x2, x3, x4 must be in a clique. Right? In other words, between every pair within these four nodes should be an edge. That's why we not only to preserve the original edge, we need to add additional edges to make sure these four variables form a clique. Okay. So this is called marrying parents or moralization. So you can follow this rule to convert any directed graphical model to undirected model. Okay. And usually you have to add more links to conduct moralization. However, if you have a definition of probabilistic graphical models, an undirected graphical model, right? P of z like psi 1, 2, x1, x2, and psi 2, 3, x2, and x3, right? It's hard to determine the edge, the direction, right? It's hard to convert it back to a directed graph because you wouldn't know this potential function particularly corresponds to the product of which set of conditional probabilities. So that means it is straightforward to convert a directed or Bayesian network to an undirected graphical model, but it's not vice versa. However, does it mean like undirected graphical model are more expressive than directed graphical model? And the answer is actually is no. So here is like family of probability distributions that can be represented by directed graphical model. And here are the family of distributions that can be represented by undirected graphical models. They have some large overlapping part, but in both family, they have some members which cannot be covered by the other. So here we give the two examples. First, from this head-to-head structure, the Bayesian network, we know that condition on empty set A and B are independent, right? But condition on C, A and B are not independent. If you convert it to a undirected graph model, you cannot have these two properties hold simultaneously. And if you look at this undirected graph model, we can claim that condition on nothing, A and B are not independent because you have at least two paths connect A and B. Right? And condition on C and D, A or B, A and B are independent. And condition on A and B, C and D are independent. You cannot construct any Bayesian network which satisfy the three properties simultaneously. I mean, I highly encourage you to try this and verify this conclusion. Okay, so now we have finished the introduction about the general definition of the graphing models, right? We covered two types of graphing models. One is called directed graph model Bayesian networks, and the other is called undirected graph models. This is usually referred to as Markov random field. And we talk about how to convert a Bayesian network to a Markov random field, which is called moralization, because you have to. The reason is that you have to ensure that your undirected graph model is defined on clicks and maximum clicks. That's why you have to add additional edges to ensure they are in a click. And the Bayesian network is an acyclic directed graph. The reasons is Bayes rule. And if you have a cycle in Bayesian network, you actually cannot finish a valid probabilistic sampling procedure of the random variables. And what's the definition of conditional independence, right? How can we test the conditional independence for any two sets of random variables, given the third set of random variables? We talk about three basic structures, right? And we talk about explain away effect, right? And we call about baseball algorithm, right? Which is kind of very effective and very efficient algorithm to tell the arbitrary condition independence. And also, Bayesian networks are not equivalent to Markov random fields. Markov random fields are not equivalent to Bayesian networks. They both can represent a large family of distributions, but there are distributions that Bayesian networks can represent, yet Markov random field cannot, and vice versa. So any questions so far about the definition of graphing models?
First, I think that we can now, it means that we can convert any undirected to directed and vice versa. But we don't mention that it's not defined. Every Bayesian network can be represented by a Markov field.
You can convert any directed graph model to an undirected graph model, that's for sure. But does not necessarily mean that every probabilistic model represented by that doesn't necessarily mean the family of distributions represented by this by a specific directed graph model is the same as the family of a distribution represented by the undirected graph model. Does it make sense?
The family distribution.
Mm-hmm.
If you convert the Bayesian network to Markov random field,
Mm-hmm.
you converting the product distribution may change.
Mm-hmm. So that means, okay, you can convert this distribution to this graph, right? So that means, okay, I got this, right? But that does not mean like these two families are the same. They're not the same.
My question is, is it these two family of distribution are equivalent or not? you can you convert in Bayesian network to Markov Blanky and do the inverse?
No, cannot do reverse. What?
So your point is down here. The family of distribution can be represented by Bayesian. The subset of the family of distribution can be represented by. Right.
Oh yeah. Yeah, but for this you cannot find. You cannot find any Bayesian network that satisfy this the three properties. Yeah.
One family distribution.
Yeah.
Have some distribution that cannot be found.
Yeah. I would say well, I think you hit a very subtle point. That's very good, but I wouldn't say like, for example, this distribution form falls into the distribution form of the undirected graphic model, but that does not mean every property will be satisfied. If you look at this graphic model, right? If you convert to the undirected graphic model, we can now see this way. Although this form can still represent the probability, but it cannot guarantee that in any instance of this Bayesian network, when it is converted to the undirected graphic model, will satisfy these two properties simultaneously. So this is just a abstract form match, not including all the specific properties. Yeah, that's a very good point. But here I just want you guys to know that when we drill down to the specific properties, we're talking about this property will satisfy for every specific distribution that's represented by this Bayesian network. However, when you convert it to the undirected graphic model, for some distribution, no, then you cannot guarantee. For the undirected graphic model version of this, every distribution will satisfy two properties. So this is a subtle point. Does it make sense? Okay, any other questions regarding the definition about this and the basic concepts about that? Okay, so we're gonna now talk about the very important part. Given the model representation, right, we have a family of models which you can flexibly represent a bunch of distributions, right? And that means we have a powerful tool to express the relationship between the random variables. But our problem has not been solved, right? We have this tool for the representation. We need the tool to calculate, right? Given the data, how can we infer different probability, the probability of different nodes, the distribution of different nodes? Right? So then we need to talk about how to conduct inference. Right? So inference here is like training, is like prediction. It's all the things that you need to calculate to obtain some quantity of interest. This is called inference. So so sometimes when we call training, it is also called inference. Sometimes we call the estimation is also called inference. So in the probabilistic world, people like to use inference, but it has nothing to do. I mean, it's nothing different with estimation, training, prediction, all kinds of stuff. Okay, so what's the general task for inference? One sentence. We want to compute the posterior of one or more subsets of nodes given the observed nodes in this graphic model. So, for example, given this graphic model X and Y, And this is a graphic model. And we know that in practice, we have that model. We also have observed data. Right? So observed data are corresponding to some nodes in this graphic model, like y. And then suppose y is observed, then our task is to compute the posterior probability of the remaining nodes given observed nodes. And according to Bayes' rule, we know that this conditional probability is the joint probability P of x times P of y given x divided by the joint, divided by the marginal probability of y. Okay? So the joint probability is relatively easy to compute, right? Because when we specify the graphic structure, we know, okay, the joint distribution should be decomposed in this way, okay? And it should be easy to compute. Then the major issue is to compute the marginal distribution of the observed nodes. Like suppose it's y. If we want to compute the marginal distribution y, we have to marginalize out y in the joint distribution. Right? So maybe in this case, we feel it's relatively easy. But imagine you have a lot of nodes, right? You have thousands of nodes. You have a graphic model, you have observed 10 nodes, right, in this graphic model. Right? How can we calculate the marginal distribution of these 10 observed nodes? You have to integrate out the other hundreds of nodes. This will be extremely costly in most cases. So the key is to compute the marginal of one or a subset of nodes. So here I want to use one example. Again, this chain graphic model as an example to illustrate the challenge here. So, and this is an undirected graphic model, right, just for convenience, right? We define according to the undirected graphic model, associated with each maximum click, which is a pair of successive nodes, is a potential function, which is psi1, 2, x1, x2 is for this, right? And psi2, 3 is a potential function for x2, x3, right? And it continue until psi n minus 1 n, which is potential function for the two last variables, right? And the z here is the normalization factor or the partition function. Right? So suppose those nodes are just discrete nodes, meaning that they can take k discrete states. So that means each potential function, which defined on pair of nodes, pair of successive nodes, essentially is a k by k table, right? So, and we want to compute a marginal distribution of an intermediate node, say xn, like small n here, right? Suppose xn equals to 3, right? I want to compute this marginal probability. If we do this naively, right, we know that we need to marginalize out all the other variables, right, other than xn over this joint probability. So now I want to ask, how much is the cost? K to the power of n, right? So why? Because each variable takes the k status, right? For one particular value of xn, right? You have to enumerate all possible configurations of all the other variables. So it's k to the power of n minus 1, right? And you have k possible values for this small xn, right? You have to do this k times. So k times k to the power of n minus 1 or k to the power of n, right? So obviously, the computational complexity grows exponentially, right, to the number of nodes in your graphic model, which is extremely expensive. Yeah, natural question would be, can we simplify the computation? Can we simplify the cost? So the key observation is that we can use distributive law. So like something like that, right? If you enumerate just the two variables configuration, right? Like the variable 1 will take two possible values, like a1, a2. The variable 2 will take two possible values, b1, b2. If you just first enumerate all possible configurations, multiply them together, you have many product and summation operations. However, if you can use distributive law, right? You first fix each value of first variable and adds up the values of the second variable and merge them together, you're going to largely reduce the operations. So on Thursday, we're going to talk about how can we leverage this idea to greatly simplify the computation and reduce the cost, which is called sum product algorithm. Okay, see you on Thursday.